Welcome, everyone, and thank you for joining today's session. My name is Irina, and I'm the event planner for the Redmond Reactor Space. Before we get started, I have a few things to go over. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience as well as our presenters. We encourage engagement in the chat, but please be mindful of your commentary, remain professional and on topic. Useful links will also be shared in the chat. This session is recorded and will be available on demand in 24 to 48 hours on the Microsoft Reactor YouTube channel. Which brings us to today's session. This session will run approximately 1 hour with questions throughout, and I'll now turn it over to our speakers for introductions.
Awesome. Thank you very much. Good morning, good afternoon, good evening. Hello, wherever you are in the world. Welcome to this third in our series of Jim Relearns C++, where today we're going to do a little bit of a show and tell and just kind of go through some of the things you can do with C++. So if you came to our previous streams, thank you for joining us again. Welcome to this. Please say hello in the chat. Say hello to everybody. Join in. If you're new to this stream is going to be very much for you. So please feel free to get involved in the chat, get involved in the conversation, comment on the stuff we're talking about, give us your feedback, and we'll just have a nice little conversation all about what we can do with C++. Now, I'm joined once again by Sy Brand. So, Sy, do you want to introduce yourself?
Sure. Hey, everyone. My name is Sy Brand. I am the C++ tool team's developer advocate. So I spend too much time on Twitter and make silly videos about my cats, which is what I've been doing this week. I made one of using dependent breakpoints to fix a bug that one of my cats had in his program.
And people keep talking about this. You know, if you put an infinite number of monkeys typing away on typewriters, one of them will create the words of Shakespeare. So, but this is if you put lexical analysis cat on a keyboard, they will type out.
You'll recreate the Linux kernel. Yeah.
Yeah. Nice. And NovaDev says hello.
Hey.
So hello, NovaDev. Welcome. Glad to have you with us. So I've just got the images of this cat. Just. I think there's like
I do have a video. In that video, I captured my cat like typing at the keyboard a little bit. I like held his little feet and got my partner to film it. So
you have to share that. You have to put a link in the chat. I'm sorry, you have to. You have to share. I want to see that. Because there's that classic poster, isn't there, of the cat on the computer. You know, IR programmer. I make computer beep boop.
Yes, the very like mid-2000s style memes. Yes.
Yes, that's going back, but that's classic. Yeah. Yeah. My daughter has 2 cats, and I try and avoid them climbing on my desk, but they keep trying, and they certainly love my daughter's computer. They'll literally climb on the desk and try and sit on my daughter's laptop because it's nice and warm.
Marshmallow loves sitting on my laptop. In fact, it was making just yesterday. It was making such weird noises. I was like, this is like a new laptop? What's up with this? So I had to open up the back of it and found cat hair stuck in the fan. I was like, I had this computer for like 2 months or something already. Cat hair in the fan.
Cat hair in the fans. Oh, that's funny. Yeah, this cat hair gets everywhere. So one of my daughter's cats is really fluffy, really big fluffy thing, and you know, he'll come up to me for some reason, just climb up my desk, start clawing at my leg for attention, and then when I look down, my leg is literally just grey with all this fur. So yeah, I've managed to keep his fur out of my laptops. One advantage of having a Mac actually is the fans never go off, so it doesn't seem to suck any air in to clog it up with cat fur, which is quite cool. Awesome. So today we're talking about cats. Yeah. No, I've dropped the link for that video in the chat. So go all check it out. Follow Sy on Twitter for more amusing cat videos, because the internet was invented for cat videos, I believe.
Of course, yeah.
Cool. So today we're kind of doing a little bit of a show and tell type session. We're just going to go through some of the use cases of C++. So if you came to our previous sessions, and if you did, say hello in the chat. Let us know that you're rejoining us again. If you came to our first session 2 weeks ago, we kind of looked at Hello World in C++, some of the language constructs, and just kind of get an idea of what works, how things work, how the language works, how memory allocations work, why you shouldn't be scared of pointers, things like that. Then last week's show, what did we do last week? Last week we looked at tooling. So we dug into Visual Studio Code, VC Package, and just kind of looked at how what tools you need, kind of what you can build with those tools, how you can configure them, and just how to kind of get going when you decided that yes, I want to be, I'm a C++ programming cat. What tools do I need? We kind of answered that last week, and then today is just kind of looking at some of the different things you can build with C++. Got a few demos there, and it's for you to ask your questions, and we're hopefully here to answer anything you want to know. In fact, John has come in with a question. Welcome back, John. So quick question, coming from being an old C++ programmer, can you help me understand Microsoft's view of things like the STL and Boost libraries? Oh, Sy, this is very much a question for you.
Sure. So the STL, or standard template library, or just the C++ standard library, depending on who you ask and what they call it. In fact, a tiny history lesson, STL stands for Standard Template Library, and it was so called because the original C++ template library, which the standard library is kind of built on top of, or designed based on, which was written by Alexander Stepanov, and I can't remember the name of the other author, but that's where the C++ standard library comes from. So the Microsoft view of things, or even just my view of things like the STL and Boost, is if you want to solve some problem that you could use the library for, and just want like containers and strings and the basic things that you need to get programming done, the standard library should be the first place you go. Then if you realize that the standard library is built to try and cover as many use cases as humanly possible while maintaining performance in a broad set of cases. If that doesn't work for your specific case, you have some like very stringent constraints on your platform or in some area of your code, then you can go and look at other places. So there's replacements for things which are in the standard library designed for very specific use cases. So maybe you want to look at them if you like profile your program and realize, oh, I'm having some performance issues right here. Well, I can rip out that type and replace it with something more specialized. But in general, standard library should be like go-to for most of the fundamental library types that you need. In terms of Boost, so Boost is a large set of C++ libraries, which has been going on for years and years and years, and in a lot of ways is kind of has been used as like an incubator for the standard library in a lot of ways. So a lot of things started off as Boost libraries and then were adapted or adopted into the ISO C++ standard, and that still goes on today. I would say that some parts of Boost, because it's so large and it's been going for so long, some parts of Boost are very old and outdated, and there's new things being added all the time. So if you look at Boost HANA or something for template metaprogramming, or even it's still some of the Boost like lexical stuff for string handling is still useful. Boost Spirit is still used for parsing in some places. There's a ton of parts of Boost which are very useful, and it's still being added to all the time. So if there's something which isn't in the standard library, then Boost is a good place to check for after you've looked there.
I'm dipping back into my C++ memories from years ago, and I remember Boost was where all the smart pointers were. Long before they're in the standard library, Boost was where you go to get some smart pointers. Because as we looked at a couple of weeks ago, shared pointer, unique pointer, they are now in the standard library and available to everyone.
Yeah.
So John says PJ Plager.
Yeah,
I guess that's the other
that's
standard
the
library.
other author.
Awesome. And then, yeah, John has a related question. What are a few of the best books to relearn C++? I still code, just a lot of C# and JavaScript.
One I'd recommend is Crash Course in C++ by Josh something. Something beginning with L. C++ Crash Course by Josh Lispinoso.
Yeah.
Lispinoso.
Yeah.
Yeah, that's a good one. Would recommend. It's, like it says, fast-paced introduction, assumes you already know programming. It's modern. I like the order in which things are taught in this book. A lot of C++ resources, I think, teach things in a way which they try to set up like C style things first and then go into C++, whereas this book starts with the C++, and I like that a lot.
Cool. I'm going to drop a link to this in the chat. A good one to reach out to your local independent bookstore and see if they can buy that.
Yep.
Yes, a plug for your local indie bookstore. Even though I live close to the head office of a large organization that was famous for selling books, I always go to my local indie bookstore for everything. So cool. John, you are most welcome. It's really great to have you joining us for all these shows. So hope this is good stuff for you. And as we keep saying, we love your feedback. So if there's more stuff you want to learn, if you feel like we need to do a more of a deeper dive into anything with C++, let us know, because it's a lot of fun to do this stuff. Cool. So show and tell. That's what we're doing. Being distracted by flying robots on books. We're going to do a bit of a show and tell. So I thought I might dive in first with the thing I do use C++ for. So as I've mentioned, I used to do a lot of C++ 20 odd years ago, back when I used to know what the Boost library was and things like that. Now what I do with C++ really is IoT development. And this to me is kind of one of the coolest use cases of a language like C++. It's a low-level language. It's fast. It compiles down nice and small, which means it's perfect for running on embedded hardware. So, for example, if I'm using, I'll just hold this up to the camera here, something like this. This is teeny tiny. It's an Arduino Nano 33 BLE Sense. So this little board here. In fact, what are the specs of the BLE Sense? If I can find a web browser anywhere. So this board, it has got a whole, it's got a load of stuff on there, Bluetooth and all this, motion detectors and microphones and gesture detectors and humidity and temperature and pressure detection, all that on this board with a processor that runs at, I'm trying to find the actual, it runs at 64 megahertz.
Wow.
So, you think I'm used to PCs, Macs running at multiple gigahertz. This little board here, it runs at 64 megahertz. Adorable. And it's got two, sorry?
Adorable.
Yeah, it's a cute little board, isn't it? Nice and slow and cute. It's got 256 kilobytes of RAM. Now, this is not powerful hardware. And if you think when C++ first came out, the kind of devices it was running on that it was ultimately optimized for were even less powerful than this. I remember learning to code on a ZX Spectrum, and they would write an assembly on that because it was an 8 megahertz processor with 48 kilobytes of RAM. But you think some of the original Linux machines would have been in the few megahertz, kilobytes of RAM. My first PC only had 4 megabytes of RAM. So back in the day when C++ was invented, it was very, very slow relatively to now, very low powered devices where you needed to eke out every single byte of memory. You need that level of control. Yep. So you think about a modern programming language like C# with garbage collection. How much memory do you need for garbage collection? Just be able to allocate memory and then wait until it's time to go and clear that up. and then how much CPU cycles are needed just to process running through that garbage collection. It's a lot. So running some like C# as a garbage collected programming language on a 64 megahertz processor with 256 kilobytes of RAM, it's just not happening. Absolutely not happening, which is why C++ is kind of a perfect language for microcontroller development, embedded development, Internet of Things development. So my little Arduino device here, I've got a little blinky light, because IoT is all about blinky lights. I don't know if you can see that flashing away there in different colors.
Oh, yeah. Mm-hmm.
Yep. And all that is a little bit of C code. So C++ obviously is, as we talked about a couple of weeks ago, it started off as C with classes. So you need a little bit of C code, and then from there, C++ you can add on to that. So which means any valid C program is a valid C++ program, pretty much.
Not quite anymore. There's especially because C is still they're still adding features to C, and some of them are diverging from C++ in some ways. So, for example, designated initializers are in C and C++ both, but they are slightly different in each language. There's some features which are in C, which are not in C++, like variable length arrays. You can write a subset of C and C++, which will compile as both, but C is not necessarily a subset of C++.
And this is why I love having an expert with me. Save me saying things based off what I thought I knew 20 odd years ago, and now I'm corrected. So awesome. Thank you. See, so whenever I'm on a show with somebody else, never listen to anything I say, always listen to what they say. They're usually the expert. Okay, so you can write some C code, and most of the C code you write will work in C++. I think I would say probably, and definitely what I'll be doing for microcontroller development. Again, most of that should work. I'm not doing anything truly advanced and Flash. So what I've got here, this is just an Arduino program. It's using the Arduino Ide, which is made by Arduino, the people who make the Arduino boards. And to get something that runs on this board, I need to use a low-level language. And so Arduino is kind of although it is C++, it's got its own little quirks. Things like you don't need 4 declarations, so I can actually declare things after they're used, which is a bit fun. But this is great for just managing LEDs. And when I compile my program, I don't know if you can see it here. So this is compiled down. So the whole Arduino application has got 83 kilobytes. And that's got all the stuff to actually boot the microcontroller and do everything. Now, obviously, this is not truly heavily optimized because this has got all the Arduino runtime that runs on the microcontroller, and this includes all the Bluetooth stack and everything like that. But we're talking, we're talking programs here that are smaller than the average image that you would capture. In fact, substantially smaller than a photo you would take. And to run on 256 kilobytes of RAM, they need to be that small. So you need, here you go. So when I'm compiling it, it says here, Sketch uses 83,936 bytes. That's 8% of program storage space. Because on this device, I can store 983 kilobytes. That's storage for my program. Then when my program runs, it uses 43 kilobytes of dynamic memory, leaving 218 kilobytes for local variables. So just for my program to exist in memory with all the stuff that makes the Arduino device work is 43 kilobytes. And this is kind of what's really important for microcontroller development, is knowing how big your application is. It's knowing that this is how much it sits in, because I'm scrabbling for memory. I'm not running this on my desktop with 16, 32, 64 gigabytes of RAM. I'm running this on 256 gigabytes. So I need this ability to have knowledge of the size. So when this is compiled,
and that's why also compilers have a number of different optimization flags available to them. So you can say, at quite a coarse granularity, you can say barely optimize this or optimize this very aggressively, but they also come with a thing to optimize for the size of the code, so that if you're really trying to get your code down to the smallest size so it can fit into one of these devices, then you can optimize for code size, and that will try to it won't do any of the because there's some optimizations which will actually make the code larger, like loop unrolling or potentially some kinds of vectorization, things like that. So they might make the program run faster, but they make the code bigger, and that can be a problem on these resource-constrained environments.
So loop unrolling, I guess that's where if it knows that a loop's going to run 5 times, instead of having a loop where it's jumping around in memory, it just literally copies and pastes the code 5 times.
Yeah, or it can also be, it might not necessarily know know how many times it's going to run, but it might be able to infer something about the number of times, or it might just unroll the body of the code some number of times and then surround it in a loop, which can in some situations make better use of cache and have better memory access patterns for making the most of the hardware.
Cool. That's pretty cool they can do that. You think about a lot of languages like Python, which just runs through line by line. This is the compiler actually trying to make smart decisions on how to build up your code when it converts it to the machine instructions. I guess it's like inlining as well, because that's something you can do in C and C++. You can mark functions inline, which means don't call this function, don't do that extra step of jumping into another area of code, but literally copy and paste this block of code into everywhere that it's used to make it slightly faster.
And the compiler will do that by itself in a lot of cases as well.
But again, if you're compiling for size versus speed, it's not going to do that, is it? It's going to not inline things because that takes up more space.
Yeah, or it will take that into account in its heuristic, because most optimizations are based on not objectively this is the best thing to do for the code. It's heuristics, because you don't know what the program's going to do at runtime most of the time. So the compiler will say, okay, well, if we're optimizing for size, maybe we'll inline just this one because it's small and we think that we don't want to have these branches going around. But this inline block, this would blow up the code size quite a bit, so we're not going to inline this one. It's taking it into account in the decision making rather than saying, okay, I'm not going to do any inlining because we're optimizing for size.
So compiler kind of a bit smarter than just following a set of dumb rules. It tries to work out what is the best option each time.
Yeah, optimizers can do quite amazing things these days.
I do remember, and this is going back some, where I had a bug in some software developing. So this is back 20 years ago when I was a C++ developer, and it's only in release mode, not in debug. So it's something to do with the optimizer, because when you compile your code for debug, it doesn't optimize it because it needs to literally be able to map line to line from the code you've written to the actual output, so you can step through that code. But yeah, so only in release we did it. So we had to put things like logging statements in to actually kind of track the bug through logging. And as soon as we added a logging statement, the bug went away.
Yeah.
And take it out, and the bug comes back. And so I think we actually got it down to we just needed to declare one extra variable inside the function, and the bug went away. And so it's just
sounds like undefined behavior to me.
Yeah, I had no idea what it was. Be something the optimizer. I mean, this is going back some. So we fixed 20 years of compiler bugs since then. But yeah,
I mean, it's likely that could have not been a compiler bug, but your program had some undefined behavior, and the optimizer was thinking, oh well, this thing in the program can't happen because that would be undefined behavior. So we're going to optimize based on the assumption that it doesn't do something illegal, but then your program does do something illegal and then falls foul of the optimizer. So it could have been that the optimizer was completely within its rights to make those optimizations, but it was just there was an issue in the program. And we have things like sanitizers for catching these now, like UBSAN for catching undefined behavior. So that we have better tools available to find these issues now,
which 20 years ago we just didn't have. I mean, it's not something we'd ever see the compiler spit out as, this is undefined. It's not something we ever used to see. So it's great that the tools these days are so much better at catching Jim's dumb mistakes.
Yeah, any mistake you can catch at compile time before it becomes a runtime failure, or even worse, of behavior change at runtime which doesn't crash, then that's all the better.
Yes. Yeah, it's an old graph, isn't it, of the amount of effort to fix any issue. It's literally at developer time and testing time, production time, and all that. And yeah, it's literally if you don't if it's just your compiler just spots it straight away, that saves you so much time and effort.
Yeah.
So yes, this is kind of just a basic Arduino program, and although we'll just zoom in here, it's called an INO file. It's an Arduino sketch, but it's essentially a C++ file, and this compiles, and I can bring in other C++ code into my Arduino library. And this is kind of the space I play in a lot whenever I do C++. I don't do anything particularly advanced. I'm setting a pin to be output for an LED, and I'm writing code to the LED. Not particularly advanced, but this is kind of one of the great use cases of C++. Now, if I just pick a slightly more advanced one, I have got a more advanced Arduino program here. And if I bring this up to the screen, you can see it. Look at my spinny thing.
Oh, cool.
It's pretty cool. So this is a Seed Studios Wio terminal. And although it's slightly bigger and it's got a flashy screen, let me see if I can get the specs for this one. It runs at 120 megahertz, but can boost up to 200 megahertz and has 192 kilobytes of RAM.
Wow.
So again, it's, compare that to the other board at 64 megahertz with 256 kilobytes of RAM. It's very, very underpowered, and it's driving a screen and Wi-Fi and, a whole lot of sensors on board. So same thing. I need that low-level programming language that's going to optimize for everything I do. Now, the tool I'm using here, I'm inside Visual Studio Code here, using a thing called Platform.io, which is it's a developer tool for embedded development. So it knows how to program using a whole lot of different frameworks for microcontroller development, whether using an RTOS, a real-time operating system, using Arduino, whatever. This can do that. Under the hood, it just calls out to whatever C++ compiler is recommended for the particular hardware that you're using. But one thing this does do is allows this so I can bring in these Arduino libraries. So Arduino, the whole Arduino framework, provides you with libraries you can use. We looked at VC package last week, but if you've done pip for Python, NuGet for .NET, similar idea. I can just bring in an Arduino library. But one thing with things like a NuGet package is you actually get the DLLs, you actually get the IL code, and you may be only using 1% of the code that's in the NuGet package, but you get the entire package. Now, we're talking about 192 kilobytes of RAM here. So I'm bringing this Arduino library for the LCD. This is for the screen. I don't want everything. I just want the little bits that I need. And so if I actually look at what Platform.io does and the way Arduino works, is it brings in the raw code. So it actually brings in all the source code into here. So framework Arduino, and here's the actual source code. That's for
those look like the object files.
Yep, I'm clicking the wrong place. Sorry, I was saying to Sy this morning. My daughter was up last night for an hour, so I was up with her for an hour, and then I was wide awake. So I'm running on not much sleep and far too much coffee. So if I carry on saying stupid things, I blame it entirely on lack of sleep. So yes, Platform.io brings the libraries, and here it is, the library here, and it brings it in as essentially the source code. It kind of takes the whole GitHub repo and drops that into my project. So I've got TFT drivers, and there's all C header files in here. User setup header files, so all the code's in here. So when my application compiles it, it's not just dropping in a pre-built library. It's actually recompiling the code. And that means I can it can take advantage of the linker to strip stuff out. So this might be a good time. Sy, do you want to explain what the linker is and what it does?
Sure. The linker is basically so that the compilation workflow in C++ is generally you have a bunch of source files, and each of those source files gets compiled into a single object file. Not just the source file, but the source file include and everything which it hash includes. We call that a translation unit. So this outputs an object file, and then the linker is responsible for taking all of these object files and any other static libraries or dynamic libraries and putting them together into one final output. And the linker can do a bunch of clever things. Like for one, if you're just compiling to an executable or static library and you're only linking together static things which it knows about and which it can see you're calling, then anything you don't call within that, it can just throw away. So any symbols which are not referenced in the entire program can be stripped. Another very clever thing it can do is if you have compiled absolutely everything with the same with the setting, it can do what's called whole program optimization, where that first compile step is not actually compiling all the way to an object file. It's actually compiling to some intermediate representation or like some bytecode type thing. And then what the linker does is it gets everything together and then it calls back into the compiler to generate the final program. And what that means is it has the entirety of the program visible to it while optimizing. So it can do things like do inlining across source files and do more aggressive optimizations, which it otherwise wouldn't be able to do because it just wouldn't have visibility into the code. So there's a lot of really interesting stuff in linkers, even though they carry so much legacy with them, because the linking, the way that symbols are linked together in C and C++ has been like essentially stable for. I don't want to get too much into this, but they have to care about how they link against C code and things like that, so they can't change the linker format. So people have put a lot of work into making linkers as fast and clever as they can while still fitting into these old linkage models.
So that is pretty cool. So it can literally, because it's compiling this code here. If I did have, so as you say, some static libraries from somewhere else, it just goes through, just rips out everything it needs, just what it needs, and helps it get it as small as possible. The teeny tiny. Again, thinking about the fact we've got a limited amount of space on my device to put it. It needs to be that small. And you compare that to, one example is a popular social media app that you can get on your phones that uses a JavaScript framework, and it's multiple gigabytes in size for this application, I think, because they've literally replicated the code in so many different places. They brought in this library that's got all this code, and this library's got all this code, and it's so big that they've even released a cut down version of the app to run in countries where they have lower bandwidth, because it's just loads and loads of wasted space replicating code. Of course, you don't get that with C++, because everything that's not used is stripped out. Which begs the question, I guess, reflection. That's just not something C++ could ever do.
Well, not necessarily. So we're getting static reflection in C++, i.e. reflection at compile time. So asking questions about your types and things like that at compile time and generating code based on it. So you could make a runtime reflection system out of that simply by saving all of the data which you need into some runtime data structures and then using that at runtime. So it definitely is possible, just with you need to decide, where you're going to store all of this stuff at runtime and how you're going to reference it and make use of it.
They just come to the whole dynamic thing of you declare code that's only ever used because you reflect and look through the assembly and just say create one of these, the same as you could do in C++. That just wouldn't work, because if there's no if the code's just not there, because it's not, the compiler doesn't see it ever being used, then it'll just get deleted. So if it's something where it used some kind of configuration file to tell which classes to load up, because that configuration file is not compiled, then the code's just not there and it just wouldn't work. So,
yeah, if there's something which you need for runtime, then you would need to manually save it aside somewhere.
Yeah. So it's I guess it's like with any programming language, it has its upsides, it has its downsides, it has use cases, and it has things you can't do. So yes, if you wanted to custom load DLLs with that may not work, but then again, I can compile this down to a few kilobytes in size and run it on a teeny tiny microcontroller. So we've had a question come through, and unfortunately, this is not one I'm afraid we can help with. Cloud Guru 2053 asks, what do you recommend for Azure AVS regarding the load balancing internal and external in the same region? Clarifies around AVS is Azure VMware Service. Sorry, that is way outside of what we're talking about today. We're talking about C++, the programming language, and that's not something that I would even have a clue about. So apologies, this is not the right show for that particular question. This is absolutely no idea about the Azure VMware Service. But reach out to me on Twitter. I'm on Twitter at JimBobBennett. Reach out to me and I'll see if I can connect you with some folks who actually know things about Azure VMware Service. So, apologies. This is just not something that we are covering in this particular session. This is a programming language session. So, but please reach out to me on Twitter, JimBobBennett, and I'll see if I can get someone to help answer your question for you. Cool. So this is a bit more of the IoT stuff. I do want to just touch into very briefly an RTOS. Where's my RTOS? Now, if I press the right button to zoom in, that's the wrong button to zoom in. There we go. So with the Internet of Things, we're running on very small, very constrained devices. And we can't run a full operating system. You think about Windows, Linux, they take a lot of power. So we just think about a constrained device. So if I wanted to have an operating system running on a small IoT device, I would kind of need an operating system I could compile in with my code. Kind of going back to this idea of I need a linker to kind of strip all the stuff out. I need something I can compile it with my code. And so that's kind of one thing that IoT devices can have is they can have operating systems called real-time operating systems, RTOS, RTOS, that allow you to kind of compile the OS into your code and provide you with some of the basic things that an OS gives you, like kind of preemptive multitasking. So the idea of it can have multiple threads and it just works through running the code in each thread, depending on how the kind of priority of that particular thread. But so it's just, so not going to dive into this too much, but just if you do want to run on constrained devices, then you literally get an OS that you compile into your code. Same idea as I was doing with compiling in the LCD library to get my little spinny thing going here. To run an OS on a little board like this, a little development board, I need to compile that in. So I've got some code here that compiles in a real-time operating system, and all the code for the real-time operating system is just in my repository. So it can't be hidden. All the C code is here. I just download the code and actually compile it in. So if you're an IoT developer, the operating systems you need to build those in. So that's Internet of Things stuff. That's kind of my area. But I guess
we've just a quick note on those is we've been adding some support in Visual Studio for help for RTOS and embedded. Like there's now an RTOS objects if you're in Visual Studio. We recently released a embedded extension for VS Code. We've added some additional register views to Visual Studio for doing embedded as well. So there's a bunch of stuff going on in that area and the tooling.
Yeah, because when you're optimizing for these teeny tiny processes, you kind of need to be able to get right into everything, don't you, to see what's going on. So, debugging it sometimes does mean just looking at what's in the registers, because you can't run a standard debugger necessarily against your code. You think to run a debugger against C++ code, you build it as a debug version. You have a program database with the maps between the lines of code and the actual compiled code, but that's huge. Compared to the fully optimized code. So you can't do that on a small microcontroller because there just isn't enough space on the device to put the debug version of the code. So you kind of almost have to step through it at the assembly level, don't you? So you need to look at the registers, the short-term memory pools inside the processor, see what's going on, because otherwise you've just got no hope. So it's cool that we're adding all these features. That's really cool, actually. I didn't realize we had that in Visual Studio. I normally use the Platform IO one inside Visual Studio Code, but something. I guess that this is my homework for the week, is to actually play that in Visual Studio, find out how that works.
Yeah, let me know how it works.
Nice. Cool. So let's move to look at a quick look at real-time operating systems. Don't want to spend any more time there. Let's look at desktop stuff. And I know one thing that came up was a question I think it was last week, was how do you interact between .NET and C++? And it turns out you can. Turns out you can do this. Turns out there is C++.NET. So do you want to dive into this side? Do you know much about how all that works?
Yeah, so this is C++ CLI, or like managed C++, which is like a bridge between C++ and the .NET world. So you could have parts of your code which are written in pure C++, and you could have parts which are written in C# or something, and then you can have a bridge between them using this, which is kind of like an extended version of C++. You see these carets; those are like that says that this is something which is managed. This isn't like a native C++ thing which just lives on the stack or somewhere on the heap. This is something which is managed by the runtime.
So you think of this is basically the managed version of a pointer, essentially, isn't it? So where you'd have char star, this little caret thing says is the managed version. And by managed, what we mean is the memory of this is managed by the garbage collector. So this is managed by the whole .NET garbage management system. So we don't need to worry about creating unique pointers or shared pointers or anything like that here. No new, no delete. We can just create one of these and it's managed for us. And then we can just call into the standard .NET libraries. And we think this is a hello world program. If you've done C#, you would do using system, int main, system string array args, console write line. This is exactly the same as what you'd look at this and just recognize this as .NET. Console.writeLine, this uses the .NET standard library console write line function. It's exactly the same as we get in C#. And if I run this will spit out to the console. So I guess the power of this then is, as you say, you can compile in normal C++ with, there we go, hello world, yay, all works nicely. You can compile in normal C++ with managed code. So if I had a whole load of really cool C++ libraries, that did financial modeling or, machine learning or low-level graphics or something cool like that, I could just put a .NET wrapper on top of it, and then people could write code against it in C# or F#. It's kind of basically what we're doing here, isn't it?
Yeah,
that's pretty cool. That is pretty cool. So, because a lot of languages kind of have this bridge to C, don't they? It's kind of fairly standard thing to get a way to call into C libraries. But it's allowing me to expose my C++ code to the outside world, which is nice. John has a question on this. How cross-platform is managed C++?
So this is Windows only.
Okay, so not cross-platform at all. This wouldn't work with .NET Core running on Linux, for example.
Yeah, I don't believe so. I've never worked with that, but my understanding is yeah.
Okay. Yeah, I've never heard of it with .NET Core. When we talk about running .NET on Linux, mostly it's just C# and F#. So okay, Windows only. Boo, but it's still cool that we've got it.
Yeah.
Now, question says, what Windows model does it use for Linux, since there's no Win32?
Yeah, I think that's assuming that it would work on Linux, but it doesn't. So
yeah, so you can't use things like WinUI or Windows Forms or WPF, because that's all OS level stuff. So yeah, doesn't work. So yeah, because that I guess that makes a lot of sense, because part of the standard libraries have got that. You wonder with Maui, with .NET Maui, whether there'll be support for C++. Because maybe I have to ask the Maui team. So Peter asks, what's the difference between C++, CX, and C++ CLI? I recently learned that in one of the two, there is actually some unseen COM in the background.
Yeah, so this is something which I don't have a lot of knowledge on. C++ CX, I believe, is for like interfacing with the Windows runtime, and is mostly being superseded by C++ WinRT, which is like a C++ 17 language projection for the Windows runtime for C++. And I have played with C++ WinRT at the moment, but yeah, I can't speak too much to C++ CX.
Okay, but with C++ CLI, is there COM in the background?
I couldn't tell you. I've never played with it enough.
Yeah, so COM's the component object model, and this is really going back into my Windows programming days of a very long time ago, and that's kind of how a whole lot of the different parts of Windows communicate with each other. It's how you can build shared code that works across all different parts of Windows. You can kind of register applications with a system that provide COM objects that you can then reuse. It's kind of code reuse, cross-language, cross-application. It's kind of the underlying technology of how you could embed an Excel document into a Word document and kind of things like that. Going back to OLE, object linking and embedding and all that. It's kind of very old stuff. But yeah, so definitely with some of the C++ stuff, you can interact with COM. And I'm guessing with this, C++ CLI, you would better interact with COM objects.
You definitely can in C++ WinRT. You can.
Okay. So C++ WinRT then, if I actually go to a Windows application, this is kind of getting a bit into the Windows weeds here. This is C++ with Win32. So this is really going low level. So Win32, this is the underlying Windows API. It's called Win32, but it does run in 64-bit on 64-bit Windows. So I gather. So it's actually Win64, but it's not called Win64. It's still called Win32. But this is kind of the underlying C++ libraries that Windows was built with. I think it's going back to Windows NT.
Yeah.
Going back to some of that. So, and this allows you to get really, really low level. So if I just run this application up, okay, this is, there you go. It says hello world. So how many lines of code, it's a question for you, Si, how many lines of code do you think it takes me to do a Windows hello world application?
In Win32, I haven't done that in so long. Maybe 200, 150.
150 to 200. Let's see. Not bad. 182. Yes, nice. But yeah, this is the real low level Windows stuff. So, we've got this API entry wwin main. So there's lots of W's everywhere, which means wide usually. So this is using like 16-bit pointers instead of 8-bit pointers, or 32-bit pointers to 16-bit pointers. Kind of, as the pointers have got bigger, as they kind of gone from 8-bit Windows, 16-bit Windows, 32-bit Windows, 64-bit Windows, they have this idea of long pointers and long results and wide things where it's 32 bits rather than 16 bits or something.
This is string handling because Unicode, all of the Windows stuff doesn't use UTF-8 like everything else. It has a lot of history with like UCS, whatever, and yeah, so string handling on Windows, you have to be careful if you're interfacing with like UTF-8 stuff coming in from wherever else.
Right, so that's why it's the wide string, because each character is potentially 2 bytes per character instead of 1 or whatever it is. Wide char. That's it. It's a wide char, so it's a wide one. Yeah.
Exactly.
Cool. So yeah, this is there's a lot of stuff here. So you've got your main function, and then this is loading up the window title and the size, and you've got these H instances, and Windows is full of handles. So all this H stuff, you have an HXL as a handle to accelerator table, and you have up here, H instance, a handle to application instance. Then you have an H wind, which is a handle to a window, and these aren't kind of pointers as such. These are numbers that Windows knows refers to certain objects that it draws on screen.
Yeah, sometimes called opaque handles because they're you can't look inside them. They're just things which the API gives you and which you can give to other parts of the API, but you can't necessarily like introspect them and look at what is stored there yourself.
Because so unlike a pointer where it's a memory address, so you can literally have a look at what is the memory that comes after that address and use that to map it into fields for some kind of data structure. It's just a number, and the only way to get the information is to actually ask the operating system, hey, for handle 27, what's the thing? And there's limits to handles as well. So I remember actually going back a long time, I had an application that actually used to hit the limits as to how many handles you could allocate. Which was a lot of fun. But this is the intro. I still find this interesting now. This is how an application works with essentially a message loop, and this is how a lot of kind of operating systems sort of work a little bit. Kind of, you essentially have this kind of thing that just constantly polls for what needs to be done. Obviously, there's a whole lot more interrupts and priorities and all that kind of stuff, but essentially something saying, do I need to do something? Do I need to do something? And then checking the various places where things kind of come in. So all Windows applications used to use this kind of message pump or message loop, and then just goes through, and then inside your message loop, if I zip down here, right down here, you have this wind proc that was called, and so it'll check for whatever message comes through from the operating system. So if we have a command message so you click on a menu, show the about box or exit the application, and then WM Paint, Windows Message Paint, this says redraw part of the screen, and it can tell you what
I haven't looked at this stuff in so long.
So retro, isn't it? But you'd get back what part of the screen needed to be redrawn. So if you've got an application running, the first time it runs, it's got to draw the whole thing. But if you cover up half the application with another application, when you move this, it only needs to redraw this part of the screen to be more efficient. And it's this kind of pump. It's constantly going, working out what needs to be done. And then the core of your application is this message pump that just sits there, just chugging away, doing everything. And you've got to write all this stuff yourself. It's kind of scary low level stuff. You have to register this with Windows. You have to tell it what's happening with Windows. You have to have the icon, the cursor that you use when your mouse is over it, the color of everything. All this you've got to do it yourself, which is a lot. We're saying 182 lines of code to just pop up a hello world window, which would be 10 lines of code in C#. But this is substantially faster. So I guess this is the upside. We're really low level, so this is now really, really quick, isn't it?
Yep.
So if you need if you were writing a game, for example, using things like DirectX, which is C++ code to interact with the gaming stack, you'd do like this, wouldn't you? You'd want it to be this low level so you can squeeze every ounce of performance out of it. Yeah,
depending on what kind of game you're making, like there's a bunch of game engines which would do this kind of thing for you at the expense of would give you some of that flexibility and productivity by handling all of this low level stuff for you. But obviously you do pay for it in some ways. Always a trade-off, right?
Yes. Yeah, you want the faster you want your code to be, the more code you have to write in some ways. Oh, Muknet says, I miss the Windows messaging. Well, that makes one of us. Yeah, I don't miss Windows messaging at all. I used to know all this kind of stuff, and I'm glad I don't. I'm glad I don't have to do this anymore. Because the kind of modern version of this is WinUI, isn't it? So WinUI allows you to build apps in multiple languages, isn't it? Because this uses some of the managed stuff. So yeah, this uses Microsoft UI XAML. So it uses some of the managed stuff. It uses WinRT, which is the modern Windows runtime that started with Windows RT and went on from there or something, didn't it?
Yeah, I don't know a whole lot about the history of that, but yes, so the WinUI 3 uses C++ WinRT, which is the language protection for the runtime, and it actually means you can use C++ coroutines for writing your UI, which is really nice. You can do things like if you're, because a lot of UI stuff is fundamentally asynchronous because you don't want to be waiting for the user to open some file and lock up the entirety of your UI. So you can use asynchronous systems for this. So C++ WinRT gives you it can hook into the C++20 coroutines system for doing this stuff. So it's actually quite a ergonomic programming model for the things I've used it for. I made like a little screenshot program where you would give it a video file and it would go off and use FFmpeg to decode the video stream and take some screenshots and then give you back the screenshots in your UI, and you could like retake some of them or save some of them to disk or whatever.
Nice. And this uses XAML as well, doesn't it? Which is a markup language designed for user interfaces. And so that this will get compiled under C++ code, won't it? So we design it using essentially XML. We declare, we've got a window, we've got a stack panel, which is a panel that stacks things. And then we've got a button. And then behind the scenes, this will get compiled down to C++ code. And then when we have an event like this one, because this is the asynchronous code, when I click this button, this event gets called. So this uses the C++ coroutine to call it.
I'm not sure if that machinery would use the coroutines under the hood. Maybe it does. But you could for sure, like, there's a lot of the runtime has asynchronous versions which give you back like promises, basically, depending on what nomenclature you're familiar with, like futures or promises or that kind of thing, and you can use coroutines for chaining together actions on these.
Okay, because I guess this is going to actually be run on the user interface thread, isn't it? Because operating systems usually have one UI thread for each application. So this would run on that thread. So this would be completely synchronous code. But internally in here, if you wanted to make an asynchronous call, like you're saying, if this button loads a file, that asynchronous call would use a C++ coroutine to do that. And then, so kind of use similar to async and await in, say, C#, for example.
Yeah. Mm-hmm.
So we can actually look at the code that gets compiled, which is pretty cool. So we've got the XAML file. We actually look at the code that gets compiled. Yeah, and this is just, straight standard code just being run synchronously. Oh no, it's got one of these L's again. So this is going back to the whole Windows thing of it doesn't do strings right. So when we declare a string that Windows uses, you have to put an L in front of it. Otherwise, it's the wrong type of string.
Yeah.
Yeah, this is see here, const wchar t. So this, again, this is a bit more advanced than just a hello world. Click run, and in a minute it should pop up and we'll get a button to click. This has obviously got a lot more code in it because we got the XAML, but we don't have that horrible message pump, that 180 whatever lines of code. We're not drawing each window one by one and having to define all the details about the window. We are literally just saying
most of this is all generated for you as well, so you don't have to write it all by hand.
Yeah. So if I wanted to add more to here, I would, the C++ here that's in this XAML.cpp, I don't write this. I would go into here, into my XAML file, and then if I wanted to add something else, that's me using Mac shortcuts on Windows. That doesn't work. If I want to add another button, my button 2, something like that. I just write this, and then when this compiles, behind the scenes, the C++ file should get updated. Or maybe it won't because I'm not actually doing anything. I'm not actually writing the code for it. So if I need to add an event on here, let's add an event. If I do this, copy that. My button 2 click, for example. If I do that, then in theory, what it should do is add that into.
So I think that would be an IDE feature, and I think there should be that if you follow the right things. But yeah, I think that stuff is just support code for this. That the code which is generated from that lives somewhere slightly different in like a .g file somewhere. I can't remember. I haven't played this in a while. But yeah, you can go ahead and look at all the code which is generated by the system. Because there's things like the idle file as well there, which is the interface description language. So that will compile it so that this is like the runtime interface, so that you could interface with this component from like C# or somewhere else.
Nice. Cool. Oh, sorry, we are actually at time, but Fuel Snable. Hey, Fuel Snable's back. Hello, welcome back. IDL files, bring back ATL and COM. No. If I never see iQuery interface ever again, I'll be a happy man. Yeah, ATL COM, very kind of low-level way of doing controls and things like that in Windows code. Let's go back some. Peter Nimmo says, I miss doing ATL. No more IDL for me. Okay, so someone misses ATL. That's not me. Awesome. No, we are at time. So thank you very much, everyone, for coming. I'm just going to drop one link into the chat, which I didn't drop in earlier. There's a question about the standard template library. So there's a link to actually read up more on the standard template library if you want to learn more about that. But otherwise, yeah, thank you, everyone, for coming. I hope this has been fun and informative. Sy, thank you so much for joining me for this week, last week, and the week before. These 3 weeks have been incredibly informative for me. It's been a real privilege having an expert like you join me and educate me and help educate our audience. So thank you so much for taking your time to help everybody who's joined these streams learn more about C++. Really appreciate everything you do. Fuel Snable says, sorry.
I said thanks for having me.
It's been awesome having you here. But Fuel Snable is definitely leaning into ATL, saying ATL cool, MFC boring and dated. And then let's talk COM apartments next time. No, there'll be no single-threaded apartments and multi-threaded apartments happening here. No. So thank you everyone who's joined. If you like this stream, if you want to learn more about C++, please fill in the survey, which we're going to link in the chat. Because we want to learn more about what you're interested in, what we can do for you. So if you feel this is something interesting, you maybe want to dive more into some desktop C++ development, or there's another programming language you want to learn about, or just whatever's your feedback, please share it with us because we want to make these streams as great as possible for you. And yeah, Novadev says thanks for all. Now, thank you very much for joining us. We appreciate everybody who's joined us. And yeah, thank you very much. Hope to see you at another Reactor stream sometime soon.
Thank you all, and thank you to our speakers. If you're interested in joining Jim Learns Stuff episodes next month, he will be back. I have shared the link to our meetup page in the chat. We look forward to seeing you then. Until next time, thanks everyone.
Bye.
Bye.